In the previous example, a time-invariant unit source calculation was used to demonstrate the dose calculation using con-to-rem to apply the emissions, decay, and dose calculations. In this example, following a procedure like the one used to create a multi-file transfer coefficient matrix, but including the two unit source computational species used in the previous section, we will generate a one-model simulation for each emission period. Then we use condecay with multiple species defined on the command line to create concentration files with multiple species for each emission time from the two computational species. The con-to-rem program is then used to convert the contents of each file to dose. In addition to the dose t-emit script and the WRF meteorology file, two additional files are required for this simulation: a special activity_unit.txt with unit emissions rather than the actual rates, but with the dose conversion factors for each species, and a file called cfactors_all.txt with the time-varying emissions for the top 10 radionuclides. Comparing the contents of activity and cfactors files, you will find the unit emission rates defined in activity.txt, while the cfactors file is just an expansion of the previous activity file, but to include all the remaining important radionuclides. These issues will be addressed in more detail during the post-processing discussion. As in the previous example, in the setup.config nameless file, we define the variable maxdim equal to, which means that both pollutants, N-gas and R-nuc, the noble gas and small particulate radionuclides, will be assigned to the same computational particle. The two pollutants, N-gas and R-nuc, are defined as such in the control file, with a unit emission rate for the duration of the simulation, and with the appropriate defaults for dry and wet deposition. The model simulation is repeated 24 times, every 3 hours for 3 days, with the run duration shortening by 3 hours after each simulation. A custom control file is created for each loop iteration. After all the model simulations have been completed, 5 post-processing steps are required. As each step is reviewed, you should refer to the illustration, the first illustration, to follow the file conversion process. In the first step, condecay is used to apply a time-varying release rate as defined in cfactors_all.txt to the 24 TG files created by HiSplit. A computation loop is not required, as the program automatically looks for file names according to the dates available in the cfactors file. The program associates the column number in the emissions file with the species index number in the HiSplit file, and applies radioactive decay from the decay start time according to the half-life specified, assigning the radionuclide species as indicated in the label field. We are only using 10 of the 14 radionuclide species defined in the cfactors file. This means that each TG unit source dispersion coefficient can generate 10 species in the CG output file. For example, In the last conversion for xenon-133, column 14 is associated with computational species number 2, N-gas, as defined in the control file, which has a half-life of 5 days, and will have an ID of X133 in the CG output file. All other radionuclides are taken as particles and will use the computational species number 1, R-nuc, for their calculation. The next two steps are run in sequence in the loop of file names for each starting time. The first step, using con-to-rem, involves processing each CG concentration file and matching it to the same radionuclide ID, the -S1 option, to compute the dose. This requires customized dose conversion factors, the activity_unit.txt file, with unit emission rates because the emissions were already applied in the previous condecay step. Also, radioactive decay is not applied in this step, option T0, because it was applied in the previous step. The process individually converts all the CG files to DG files. If you haven't figured it out by now, the file naming convention is for the prefix TG for TCM grids, CG for concentration grids, and DG for dose grids. In the next step, after conversion to dose, cont_sum is used to add together the ground shine and the cloud shine dose values using the level option from all the radionuclides in the DG files into a combined total dose output summed to the SG files for each output time. In the last two steps, the program con_merge merges the individual release total dose SG files into a single file, fdnpp.bin, representing the dose from all releases at the 3-hour output interval, using a wildcard test to create a list of the required input file names. Finally, in the last post-processing step, the 3-hourly dose values are summed together, the R1 option, using the program con_avg_pd, con_averaging period, to obtain a total dose over the specified averaging time defined as the period between the A and B command line arguments. Start the simulation, and after it has completed, continue with the post-processing and output graphics. Your temporary or working directory will contain all the intermediate files. The graphics, as in the previous example, shows the 3-hour dose values at Tokai and the spatial distribution of the dose. However, now that we are using a more realistic time series of emissions, rather than the maximum emission value for each radionuclide, the maximum dose near FDNPP is now 0.272 rem rather than the 75 rem shown in the previous example. In this case, a unit source dispersion deposition calculation with two computational species, one representing a small particle and the other a noble gas, were run for each emission period over the duration of the period of interest. Post-processing programs were used to assign each computational species to multiple radionuclides, each with its own emission rate, decay, and dose factors, to compute the total dose.